I'm really glad everyone is here. We got such great speakers and such a great audience. So I would like to kind of welcome all of you to this first QRE community meeting. And before anyone gets confused, like, hey, I signed up for a talk and not for a community meeting, like what's going on? Yes, this is talk. This is like the biggest part of that is talk, but we're also trying to build some community around QRE related topics. So I would like to just first do a brief introduction to kind of this like initiative that started recently. So that is first, then we'll have a talk, then like some discussion, and maybe we'll get to some discussion of like how people want to get involved with some of the community initiatives at the end, but absolutely it's mostly about the talk today. So I wanted to first start like why did like some people came up with idea of creating this like QRE community. So like first, why QRE? Well, because we, together with like some other people, we organized workshops around quantum resource estimations, and I think it was very successful and very interesting, and like there's a lot of enthusiasm in the people, so we wanted to capitalize on that. Second thing is that like QRE is to me a bit more concrete than algorithms or applications. These terms can be very, very broad, and I would like to like start from something a bit more specific and concrete in kind of building this community. And there is both. So for example, for QRE, we have both tools and also kind of research going on. For a lot of algorithms, it's like hard to even talk about tools because I don't know, there's like definitely for fault-tolerant algorithms, they're not as developed. And also, well, it's just like some place to start, right? Like it might turn out to be quantum algorithms community like 2 years from now, and like we'll have very little QRE component. I don't know, we'll see. We're just like, let's get started. And why even community, like creating community? So like first thing is it's great to exchange knowledge with other experts in the field. It's a great place for people who are developing tools to connect with people who want to use these tools, and like people who might want to use the tools to actually learn that they're like any tools. We can work together on figuring out like what language we want to speak, what like certain words mean, because there's a lot of confusion in a lot of quantum computing subfields on communication. But also like give opportunity for some junior members to learn, to get idea for what a good project is, how to kind of learn more about the topic, and just in general, hey, it's nice to kind of hang out with people who work on the similar stuff and like be friends and kind of just have some flow of information and not work in silos. So how to engage? Please, whoever is not on the Discord, please join our Discord. I will send the link in the Zoom chat. And if you want to help with doing anything, please just like ping me and let me know how much time you have to spare. Is it like, I can work on this full time, or I just want to, I don't know, help with something. I have 1 hour on Mondays, whatever. Just like tell me what's if you want to help, how you would like to help. So far, the initiatives that like we started here are organizing talks, and this is the first talk. There is some discussion on the writing blog post with Unitary Fund for open source quantum resource estimation tools, and also we already had like some valuable technical discussions on the Discord, so that also is nice. Some other things that are also being discussed is we would like to create, or like we would like some wiki like thing about like quantum subroutines. Like the nickname for now is like cornucopia of quantum subroutines. So this is something that also Alex and Sam did in their paper, like try to categorize some of the subroutines and describe them. There are like some conversations going on about the data structures for representing fault-tolerant quantum algorithms, and also I think Maria suggested that maybe it would be a good idea to maybe do some online QRE workshops. So if any of these looks interesting and you would like any of these things to actually happen or help with, then please let me know and we'll kind of try to do this. Even though, you know, I kind of started the thing and I'm organizing it, I very much don't want this to be Michał Stań with QRE community. I just want this to be QRE community, so I want other people to engage. And okay, that's enough me talking. Took me 5 minutes. I think that's okay. So I'm giving it to Alex and Sam. So for those who don't know, Alex and Sam work at AWS on quantum computing algorithms and applications. And they recently released a really great review on the topic. So the floor is yours.
All right, cool. Just share the screen. Okay. Does it look okay? Okay,
yep.
Cool. Yeah, so hi, I'm Alex, and Sam is also here. He's gonna take over partway through, and we're talking about this algorithm survey that we put on arXiv a few weeks ago, and kind of made together with a bunch of other people listed here. And yeah, so yeah, we're excited to talk about it. We're excited for this QRE community to come together. So hopefully it can help. Let's see. There we go. Okay, so yeah, the agenda today. I mean, obviously it's the survey paper. It's not really about a specific result. So, you know, we don't want to focus on one or two specific things. But yeah, so we're gonna kind of talk about the high level motivation and goals for the survey and kind of like how we view quantum algorithms in that context. Just briefly kind of mention what's in the survey and how we think people should use the survey or how we use it for ourselves. Then Sam's gonna go through like a complete example of how a good way that it can be used. And then we'll conclude with sort of a list of things that were not covered and open directions. Yeah, so the motivation, I guess, I think we can kind of think about the field of quantum algorithms, and there's sort of some good things going on and some bad things going on right now. I mean, on the good side, you know, I think the field of quantum algorithms is much more mature more mature than it's ever been before. And, you know, sort of 30 years ago, we didn't really know any quantum algorithms, but now we have a lot of very well developed and optimized, you know, algorithmic primitives, and we've combined these into you know, larger quantum algorithms that can solve concrete applications in industry and science. And, you know, also we're building devices, and, you know, we can imagine building fault tolerant devices. You know, there's sort of nothing stopping us now feeling right now. So, you know, this is sort of a good situation to be in. But on the other hand, these quantum algorithms that we have are kind of very complex, and there's in order to kind of understand which ones will be useful, you really need to understand every layer of the stack very well. You have to have a lot of domain expertise to do these resource estimations, which I guess this community would be interested in. You know, you need to really understand what the algorithm is doing. You need to understand the error correction. You need to understand the hardware. So there's sort of a lot of things going on, and it's hard to have a full picture of it. Also, you know, when you do go through that process and you produce a resource estimate for these algorithms, often the result is very far from what we can actually achieve, both because like the devices we have are very small, and the research estimates say we're going to need very large devices. But also, even if we had those large devices, sometimes it comes out to like, you know, it's going to take hours to do some kind of computation or days, and, you know, we would really like that to be better. So this is really sort of a call to action to improve these things and like reduce these counts, make the algorithms better. And then I guess, yeah, the final thing, like classical computers are getting better every year, which maybe is a good thing overall, but for the purpose of achieving advantages with quantum computers, this makes it harder. So yeah, the present moment calls for us to close the gap between you know, what we know theoretically is possible and what can be achieved in practice. So I guess, and yeah, thinking about the survey, we've kind of constructed this diagram of how we organize like the end-to-end pipeline of quantum algorithms. And I think there's kind of many ways one might conceptually organize this kind of thing. So this is just one sort of way of thinking about it. But yeah, I guess like it's important to, remember that ultimately we have to solve some application for a user, and this might be not quite a concrete thing. It might be something like, optimizing a reaction, a chemical reaction, or, improving efficiency in some kind of, optimization task, but it's not yet kind of a well-defined computational task. Sorry, forward. So the first step would be to kind of formulate a well-defined computational task that could be solved with, a classical computer or a quantum computer, and then construct a high-level quantum algorithm that solves that task, which itself is going to be made up of algorithmic primitives like phase estimation, or a linear system solver or something like that, which kind of gives the quantum algorithm its advantage. And then this, in kind of, I mean, you could try to run these algorithms without error correction, but often when the algorithms are very require many gates, we know we're going to need quantum error correction to run them. So this would have to be implemented fault tolerantly, and then that would have to be executed on a quantum device. And of course, hopefully the answer that you get out is something that the user can actually use. And this picture also allows us to kind of organize resource estimations. So, at the level of the quantum algorithm, we would compute kind of logical resources like the T count, the T depth, or like the number of logical qubits, which allows us to, once we kind of specified our fault tolerant protocol, to estimate the code distance, the number of code cycles that would be needed, and the number of physical qubits. But of course, you can't actually come to these real world parameters without factoring in the specifications of the device that you have or you expect to have, which I think you might be most interested in at the end. How much time will it take? How large of the device, like physically, will I need? How costly will it be in dollars? How much energy will it consume? Stuff like that. So I guess this picture is what we have in mind when we talk about like an end-to-end pipeline. And then, yeah, I guess with that in mind, the features of an end-to-end analysis, which is kind of what our survey is trying to go for, in how it analyzes the different applications. Like, we really want it to capture this end-to-end, all of the factors that go into this end-to-end analysis. But yeah, so importantly, it has to solve the actual problem of interest to the user, not some kind of sub-problem. I mean, I think there's been a lot of great work on optimizing primitives that kind of take something as input and produce something as output, but often these have to be combined together to actually solve the problem of interest to the user. An end-to-end analysis should count all the costs involved. This would include things like classical pre-processing and post-processing that might not be obviously something to worry about at first. It should instantiate all oracles. So often we analyze quantum algorithms with some kind of black box input, try to minimize the number of calls to that black box. But when you're thinking about applications, it's our view that we need to kind of always understand how expensive it will be to actually implement that black box. Important to note relevant caveats. Often you might have different primitives you're trying to combine, but they may not kind of go together in perfect cohesion because of some caveat. So it's important to kind of be aware of. And then at the end, you have a solution. You should make sure to compare to the best classical algorithms for the same problem. This may seem kind of like an obvious thing, but often you might have a situation where the quantum algorithm solves a problem exactly, but there might be some good classical algorithm that solves the problem approximately, and in the situations that you actually care about in practice, in industry or whatever, these approximate methods might be just as good, and so really you should be comparing against the correct classical methods for the problem you're worried about, and you should make sure to compare against the best ones. Okay, yeah, so the goals of the survey then, I guess, are, we wanted it to be kind of a navigation guide for all aspects of this pipeline, a reference for kind of state-of-the-art algorithmic complexities for different subroutines and end-to-end applications, a resource for designing new algorithms, and I guess, yeah, maybe most importantly, like a survey of all these different concrete applications, like with some attempt to organize them, You know, obviously shouldn't be viewed as completely exhaustive, but you know, I think it's nice to be able to kind of see it, all of them in one place, or see many of them in one place. And then I'll also comment that yeah, so I guess the survey has a more emphasis on kind of a fault tolerant view. This isn't necessarily because NISQ is unimportant, or it's just kind of the emphasis we were taking, because a lot of the more the algorithms with kind of more rigorous guarantees that we can kind of say with more confidence have a speed up compared to classical algorithms are often ones that, you know, we know are going to require quantum error correction. And so, you know, we hope that like heuristic quantum heuristics will be useful the way classical heuristics have been useful, but it's kind of hard to analyze them. So this is one reason we've had this focus in our survey. Okay, yeah, what's in the survey and how to use it? So the survey has 3 parts: areas of application, algorithmic primitives, and fault tolerant quantum computation. For areas of application, we cover these areas. Here I'm kind of bucketing them into a few different buckets. We don't really do this in the survey exactly, but I think it's useful to think of them this way. So the one bucket, we have like things that are related to the physical world, so condensed matter physics, quantum chemistry, nuclear and particle physics. And then within condensed matter physics, for example, we have like subsections on Fermi-Hubbard, SYK model, and spin models. And these, I mean, I guess maybe the high level takeaway of these is that there's a potential for a very large speed up under certain assumptions. You know, potentially an exponential speed up, although there's some caveats to this in specific cases. But it's kind of mostly useful for scientific purposes. And then maybe in another bucket, we have combinatorial optimization, continuous optimization, solving differential equations, finance. So these are maybe more commercially ubiquitous, but we expect the speedups to be more often polynomial speedups. Then there's like cryptanalysis, which is kind of by itself because it's one, you know, not clear exactly what the applications are, besides breaking codes, I guess. And there's like an exponential or super polynomial speedup for it. And I guess, yeah, machine learning with classical data we cover, which is kind of unique because of, you know, some things are heuristic. Often you need this QRAM component, and it's unclear kind of, you know, there's these dequantization algorithms that make it hard to compare. So this is also kind of unique. So that's kind of a brief summary of the things that are covered. Yeah, and then we have a section, a part on algorithmic primitives, where we cover things like quantum linear algebra and Hamiltonian simulation, which themselves have several subsections here you can see listed. Can see these other things that we consider primitives, like phase estimation, amplitude amplification, and then some things like the quantum adiabatic algorithm and Gibbs sampling, which might you might think of them as like full-fledged algorithms in some contexts rather than primitives. But here we kind of think of them as primitives, and we think that is sort of the appropriate place for them in this chart, in at least the way we've organized it, because you know, if you think about the quantum adiabatic algorithm, it doesn't really solve the end-to-end problem all by itself. Often you would have to, you know, use it to prepare some low energy state, for example, and then you might run phase estimation to kind of extract the energy of that state, or you might measure some observable. So really, it should be viewed as a component of the larger solution to the application. Yeah, and then finally, we have a part on fault tolerant quantum computation, where we cover like basics of fault tolerance from a kind of theoretical perspective, and then more specifically, like how do you do quantum error correction with the surface code, and how do you do logical gates with the surface code. And here we emphasize kind of the overheads involved with this and how they flow down into resource estimations. Yeah, so it kind of gives a prescription of how to turn a logical resource count into a physical resource count, at least for the surface code. And this is obviously, all of this is kind of following all the, you know, this is a survey article. We've kind of tried to synthesize and like collect all the previous work on all this stuff. So this is shouldn't be we're not advancing the state of the art in any of this. I should emphasize. Yeah, okay, and so some key features of the survey are, yeah, so like the different sections are each standalone and kind of independent from one another. They have their own bibliography, which makes the document much longer. So maybe that was not the best decision, but anyway, that's what we ended up with. It's modular, or like we kind of view it as a modular, like plug and play concept. So, you know, if you want to like change in a different subroutine, sort of easy to understand how to do that conceptually, and hopefully the document makes it easy. And it's wiki-like, so there's embedded hyperlinks and stuff. Yeah, we definitely don't recommend that people kind of read it linearly and like scroll through the document. Rather, you know, we have these like hyperlinks in the header that we, you know, when I'm reading it, I like click the hyperlinks to like go back to the table of contents and then find the new section I want to go to. Yeah, we hope people use it that way. Okay. Yeah, so I guess we'll turn it over to Sam, and maybe we could take questions at the end. So yeah, I'll turn it over to Sam here. How do I stop share?
Great, thanks, Alex. Okay, I think you guys can now see. So in the next part of the talk, I will be discussing a worked example applying some of the techniques that are listed in the survey to perform a resource estimation for the Fermi-Hubbard model. So to kind of tee this up, we can go back to this diagram that Alex showed earlier for how one runs through the pipeline of these resource estimates. But now we can instantiate all the boxes with specifics for the Fermi-Hubbard Hamiltonian. And we can really use the information that's present in the survey to populate each of these boxes in turn. So the first thing that we'll want to do is to understand the user application itself and the kind of problems we might want to solve around the Fermi-Hubbard Hamiltonian. And all of the like screenshots that I show here, not the pictures, these are just from Wikipedia, but the screenshots themselves, these are like taken directly from the survey, and they'll be popping up throughout the next few slides. So going to the Fermi-Hubbard page in the survey, we find that at the very top, there's like an overview section, which discusses like what the Fermi-Hubbard model is for people who aren't familiar with it, and some of the problems that people want to solve when they study it. And this is true for all of the sections in the wiki. They all start in the same, or the survey, they all start in the same way with a rough or brief overview of the topic that is talked about in that section. So for the Hubbard model, we see that it was originally introduced as this simple model of electrons and materials. Nowadays, people study it as a very simplified model of some high temperature superconductors. It's proven very difficult to solve this model with the best classical methods over the last few decades. And so people have suggested trying to simulate the Fermi-Hubbard model using quantum computers instead. And looking at the specific problems we might want to solve, we find that people are interested in finding the phase diagram, as shown here for the Fermi-Hubbard model, as a range of system parameters. Or we might be looking at the dynamics of the model as it's driven by some sort of external potential. So in the setting here, I'm going to imagine looking at these static properties, so trying to find the phase diagram. We're actually going to deal with a slightly simplified task of just computing the ground state energy density, so that's the energy per site, in the thermodynamic limit for a fixed set of system parameters. So we can then move to the actual well-defined computational task that we want to study by expressing this in a mathematical formulation that's suitable for being tackled with quantum algorithms. So again, scrolling down now on the Fermi-Hubbard page in the survey, we get to this part on like actual end-to-end problem solved, where we start to rigorously mathematically define what it is we want to solve and how we solve that. So for example, now, rather than saying in words, like I want to compute the ground state energy density of the Fermi-Hubbard model, we can get proper expression for the Hamiltonian of the system, which is going to be defined on M spin sites in this case. In terms of the parameters that it has, there's this hopping parameter T and the on-site repulsion term U, which is just going to describe how the fermions hop on this lattice and interact with each other and control the classical difficulty and the quantum difficulty of the problem. We can then look in the survey, which will discuss how we can map this fermionic problem onto a problem of qubits. We're just going to use this famous Jordan-Wigner transform, which will take our fermionic operators and map them in a one-to-one way to qubits, so that where before we needed M spin sites to describe the problem, now we end up with a problem that's defined on M qubits. So this is now in a mathematical form that we can just apply known and existing quantum algorithms to. So this next step is where the survey really starts to come in useful, because we've collected all of these existing algorithms that people have tried to apply to this kind of high-level problem, and show how these can be put together in different ways. So in the case of finding the ground state energy density of the Fermi-Hilbert model, there are a few steps to quantum algorithms to do this. The first is to do state preparation. So we want to prepare either the ground state itself or a good approximation to the ground state. There are a number of ways to do this, which are linked to in the survey, either things like eigenstate filtering, adiabatic state preparation, or Gibbs sampling for preparing low temperature thermal states. So that's the one that we might envisage doing in this setting, Gibbs sampling. We then need to measure some sort of energy. In this case, we're going to measure the energy using quantum phase estimation, and this needs some kind of unitary that has some way of providing access to the spectrum of the Hamiltonian. So there's, again, a number of ways that this could be done. For example, we could do phase estimation on like a time evolution unitary. But in this case, we're going to pick a qubitization unitary implemented via block encodings. Now, at any stage of running through the sequence, we might run into a term or a primitive that we're not familiar with. So perhaps in this setting, we're unsure what qubitization entails. So then we can just follow the hyperlink to the relevant subsections on qubitization, which will describe what the high-level idea of this is in terms of providing access to the Hamiltonian in a structured way that's easily manipulated. It will discuss the resources one needs for this and any subroutines it calls in turn. So what we find is that the qubitization subroutine in turn calls a block encoding subroutine. And then we might know already that block encodings are a way of providing coherent access to matrices on quantum computers. But we also know that there's a whole host of different methods that we can use to implement these block encodings, such as sparse access to the matrix or block encodings of density matrices. But we might not be certain what the best approach is for our specific problem. So again, we can follow the links through in the document to the section on block encodings. And there we'll find each of these different methods for implementing block encodings discussed in detail, both the high-level idea behind implementing them, references where these are first or prominently discussed, and the dominant resource complexity of implementing these approaches. So for the Fermi-Hilbert model, what we'll find is that the LCU approach to block encodings, that's linear combinations of unitaries, is very well suited to this problem, because as soon as we map the fermionic Hamiltonian to qubit operators through this Jordan-Wigner transform, it's just expressed as a linear combination of unitaries. And that in turn calls these two operators prepare and select, which again, if we follow even further down the rabbit hole to this LCU section of the survey, we'll find the action of these operators discussed. So at this point, things are starting to look a little bit messy. It looks like one of those crazy suspect boards where all the red tape between the different profiles. But fortunately, the survey puts it a little bit more linearly than I've highlighted here. And we can just look in detail and find that the algorithm splits kind of nicely into this state preparation aspect through Gibbs sampling, for example, and then the phase estimation aspect. And again, nesting through each of these calls, we can start to put together what the different complexities are. And for some unknown parameters like this alpha parameter here that I've not defined, this is just a normalization parameter that enters the problem because of the block encoding, but using the information in the survey combined with the knowledge we have of the Fermi-Hubbard Hamiltonian, it's not too hard to calculate what this normalization factor would be. So for the remainder of this resource estimation, I'm going to make two simplifications. The first is a reasonable one to do. I'm going to neglect this prepare oracle. The reason for this is the Fermi-Hubbard Hamiltonian is very simple. It only has two unique coefficients in the Hamiltonian, this hopping parameter t and the on-site repulsion u. And so it's quite simple and low cost to implement prepare. And in general, we can do it with many fewer gates than we require for select. So this wouldn't be the case in other problems like quantum chemistry, but for the Fermi-Hubbard Hamiltonian, it's a perfectly reasonable simplification to ignore the cost of prepare. The other simplification I'll do is to ignore this state preparation cost of Gibbs sampling. And it's not obvious whether yeah, sure, go for it with a question.
Hey, sorry to interrupt. I didn't, if it's not a convenient time, but I was just wondering, when you say gates here, you mean like T gates specifically, right?
That is a good question. Thanks for the interruption. Actually, that's really helpful. Yes. In this case, I'm just focusing on T gates. One could choose to count the Clifford gates as well. But that's, yeah, an implicit simplification, I guess I've made here where I'm counting just the non-Clifford resources. Thanks. Yeah, so regarding this Gibbs sampling and state preparation cost and whether we can safely ignore that. So this has been quite a big question in the field for the last couple of years, and there's been a few high-profile papers on whether it's fair to ignore this state preparation cost, as has been done in many of these resource estimates previously. And we don't really have a good answer to this, I think, at the moment. It's unclear whether, well, we know in the worst case, this problem of finding the ground states of local Hamiltonians should be hard for both classical and quantum computers. But in this setting where the Hamiltonian comes from something physical, it's kind of unclear whether we should expect there are settings that the classical computer can find a reasonable estimate of the ground state, such that it has good overlap with the final ground state, but it doesn't have, it doesn't solve the problem completely. So we still need the quantum computer to help. So we don't know if this is the case yet, and we don't know the resources required to solve these problems if this is the case. And unfortunately, it becomes a little bit problem specific and somewhat heuristic, which means there's less we can say about it in a kind of general overview paper like the survey. So we're not able at the moment to say what the cost of these like Gibbs sampling or other state preparation routines would be for the Fermi-Hubbard model without taking into account more specific details of the system. So for the rest of this discussion, I'll just be talking about the resources for phase estimation, as is kind of standard in this subfield of the literature anyway. And I guess I skipped ahead with that last slide a bit anyway, and the gate complexity in terms of the number of T gates has come up on the slide anyway, just by putting all of these subroutines together. So this kind of concludes the part on the quantum algorithm itself. And then we can ask, what are the resources to execute this fault tolerantly? So there's there's a number of ways that one could try and compile an algorithm to run within the surface code. And if we want to really optimize the space and time resources, then there are a lot more details that we could take into account that we don't currently discuss. But in the survey, turning to the fault tolerance section now, we give a simple worked example for how one takes these resource estimates in terms of logical qubits and T gates and converts them into a physical resource estimate in terms of runtime and number of physical qubits that we need. So the approach that's taken here is the one made quite popular in like Daniel Latinsky's Game of Surface Codes paper, where we just choose to run and apply each of our T-gates sequentially through the computation. We don't worry about Clifford gates because they're all pushed right through to the end of the circuit and compiled away into measurements. And we just imagine implementing these T-gates through multi-qubit lattice surgery applied on magic states that we're going to distill separately. All of that was a lot of detail that we don't need to specifically know here, but we can just imagine we're going to run these 10 to the 9 or so T-gates, one after another, and we need to use a surface code that has distance high enough that the chance of there being a logical error in this whole space-time volume of computation is sufficiently small. So if we take the gate counts previously, plug in some parameters that appear classically challenging, and again, these are all discussed in the survey section on the Fermi-Hubbard model, we can just crank through the handles of the various formulas, including those given within the fault tolerance worked example. And we find that with reasonable physical error rates of about 10 to the minus 3, we come back with close to 2.5 million physical qubits and around 7.5 hours of runtime for each of these energy estimates. Now, one thing to note is, this is where a lot of resource estimates in the literature would stop, but we've not really yet solved the end-to-end problem that we started with. We said we already want to estimate the energy density within the thermodynamic limit. So the things that we would also need to take into account are, well, any costs from state preparation. But as I said before, we kind of have to neglect these here. We might need to run our phase estimation a few times to account for any failure probability, which I've neglected here. And then even if this was all fine, we'd need to repeat our calculation at a few different system sizes and then perform a careful extrapolation back to the thermodynamic limit. So we can ask, once we've got these final resource estimates, how do they compare with the kind of state of the art in the literature? So we can compare against this great paper from a few years ago. Obviously, it's not a completely fair comparison because a lot of the innovations that they introduced there really helped us in writing these sections for the survey. But what we find is that at a very high level, the survey covers a lot of the detail that's in a lot of these pre-existing literature papers in terms of what the high-level algorithm is. So here, phase estimation applied to a qubitization unitary, what qubitization is, how it is implemented. This is all kind of well described by the survey itself. Once you start getting to the lower levels, so for example, implementing this select oracle for the Fermi-Hubbard model, then things start to become, depart a little bit between the two settings, because where the survey has to be written in this general way, it doesn't yet have, specific instantiations of select that would be optimized for the Fermi-Hubbard model. And as a result of that, some of these optimizations that are now more general, but were originally introduced in these kind of contexts, things like unary iteration for looping through a quantum data structure, these aren't discussed in the survey at present. And this means that the kind of resource estimate that I gave before is, mildly suboptimal for this problem. Now, for the Fermi-Hubbard model, it's a pretty simple problem, and these optimizations don't necessarily buy you a huge amount over the rough back of the envelope that we've just done. But as you get into more complex settings, like quantum chemistry, for example, these optimizations can really save you a lot of resources. And so we're still quite far from being able to take the information that's in the survey and just run through that to match the kind of state-of-the-art resource estimates that you might find in literature papers. So this kind of train of thought leads quite nicely into what topics are not covered at present in the survey, and what are some open directions for future research that Alex will return to in a second. So in terms of topics not covered, there are a few things in each of the sections of the survey. So within the application areas, it would be great to expand differential equations a bit further, because our current discussion really just focuses on linear differential equations solved using the quantum linear system solver approach. In the last few years, these ideas of quantum machine learning in the sense of learning states, unit trees, quantum channels, these questions of whether quantum learning with quantum memory can outperform just single shot settings. This has been a really exciting area in the field, so it'd be great to include some of these ideas. And then, as I said before, once you get into quantum chemistry, the field has made a lot of progress recently through these more complex block encoding approaches, ways of decomposing the Hamiltonian, like single and double factorization or tensor hypercontraction. And we don't go into this level of detail at present in the survey. So again, there's a bit of a disconnect between the literature state of the art and the understanding we might glean from reading the survey. Obviously, all these kind of state of the art papers are linked as references, so people can follow through more carefully. And we all know when we go to Wikipedia for an answer, it normally doesn't have the full explanation for us, and we have to do some more digging and follow through some references. So I think there's only so much detail we can ever expect to contain in this kind of document, but there's perhaps a little bit more of the high level ideas we can include there. But I think the largest area where it would be nice to have some more discussion would be in these low level routines. So things like simple arithmetic, so addition or multiplication, whether that's like school book multiplication or more complex approaches like Karatsuba. Similarly, these slightly higher level, but still very low level approaches like unary iteration for looping through a data structure, or coherent alias sampling for generating superpositions entangled with some garbage, but doing it in a very efficient way. And this would really allow us to get that last mile step between having these high level resource estimates in terms of algorithmic primitives and then converting these into really optimized T and logical qubit counts. And then finally, on the fault tolerance side, we're not necessarily looking to write a survey of quantum error correction and quantum error correcting codes, but there's this interesting niche that sits between algorithmic primitives and really optimizing compilings to reduce T and Toffoli counts, things like Hamming weight phasing for implementing rotations more efficiently, or measurement based on computation. And then looking further ahead, we might one day graduate from the surface code to alternative code constructions that may be more efficient for computation, depending on the architecture. And so as these are developed, it would be great to include optimizations like that as well. Yeah, so then I'll just hand back over to Alex for the last few parts. I guess I can click through the slides. You're muted right now, though.
Thanks, sorry. Okay, yeah, I guess I want to make sure to leave some time for questions and discussions. I'll try to go through the last bit quickly. But yeah, we just wanted to identify maybe some open directions for future research, like things that we weren't able to put into the survey because it's hard to identify in the literature answers to these questions. So I guess obviously some algorithms don't have resource estimations that we found. So things like differential equations, lots of these ML algorithms, some of these optimization algorithms, like solving SDPs, we wrote up pages on them, but we weren't able to quote any resource estimates. Yeah, I guess incomplete aspects of resource estimation. So I guess Sam mentioned this problem of creating a state preparation for learning energies and how this is something that often we just kind of ignore, and I guess getting a better handle on how costly that will be. So there's been some work toward this end, but it's important to flag that, I think. And then, yeah, I guess, it's exciting times in kind of quantum error correction and the possibility of more efficient codes. So this is something that we think is something people should keep thinking about. And okay, I guess next slide. Yeah. Okay. And then I guess an important one that I think maybe something I used to not really think about very much is kind of this very high level connection between what the user actually wants to do and what's output by the quantum computer, and kind of really trying to make this more concrete for specific applications. You know, I think it's easy often to kind of define a task and then say, oh, the quantum computer did the task and it's going to take 6 hours or something, but really trying to make sure that that is the full task that would need to be solved to provide value to someone. So I guess, for example, like in some of these spin models or the SYK model, oftentimes kind of we can cost out the cost of time evolution, which is could be used within phase estimation, but kind of knowing what the instance sizes are that we would need to examine, and kind of what precision values we would need to kind of learn something actually genuinely useful to physicists. You know, one thing that people may not take into account sometimes is like you might learn the energy for a certain parameter setting, but really, you know, if you're trying to optimize a reaction, you might need to try a lot of different parameter settings and get kind of energies, you know, for many of these in order to kind of learn the actual thing that's going to advance your high level goals. So kind of how many of these energy evaluations will we need? Like if each one takes 1 hour, but we have to do 100 of them, this is obviously going to lead to a much different outlook. So I think be useful to kind of make this more concrete in specific situations. So I also have an example here for optimization problems. You know, you know, we know we have this quadratic speedup for exact combinatorial optimization, but like what are the best examples where this is actually something people want to do in practice, as opposed to some sort of heuristic algorithm that gives them an approximate answer? And what are the exact specifications that we need to meet as we design quantum algorithms? So yeah, that's that slide. And then the final slide here, I guess, we can go into discussion. We'd like the document to be useful to people, and we're looking forward to hearing feedback on how it can be improved and like what, you know, a vision for like how it can be used going forward to help QRE community and others. So thank you for your attention. And let's take some questions and discussion time.
Cool. Thank you very much, guys. Like that was an excellent talk. So like a round of virtual applause for you. I think there have been like some good discussion in the chat already. So if anyone feels like just raising a hand and asking a question, we can start here. Don't be shy. Travis, great.
Sure. Hey, thanks for the talk, and thank you for the paper. It's extremely useful. So you use this phrase quantum resource estimate, and you enumerated a bunch of different kinds of categories of resource estimates. And I think I'd appreciate your perspective on what are the gaps that need to be closed in terms of understanding those categories, in terms of defining them appropriately, and in terms of helping orient the research community to like specific categories where it seems there's just a complete dearth of research going on. And maybe to be a little bit more concrete, right, but brief, right, we've got like logical qubits and T-gates and subtleties and stuff like that. We have number of physical qubits and like wall clock time for a subroutine of the algorithm. We have, how much money do I have to pay Amazon or Microsoft or IBM in order to solve my problem and get a business relevant solution? And these are all different buckets of things that we're going to require a different perspective in terms of analyzing a given sort of problem. So just would appreciate your thoughts on that.
I guess my take would be they all kind of fit together naturally. So, once we have it really feels like a pipeline in a sense that once you have the logical resource counts, I think we should probably be trying to find ways that are applicable to a lot of different problems that you can then just compile this down to, your surface code primitives, and then this can be executed, and it should return some number of physical qubits and wall time that should then just, very naturally have an energy consumption or a monetary value ascribed to it in the same way that it would classically. So I think it's, just a question of architecting a stack appropriately. So in the same way that for classical computers, you would write your program in Python and it would be compiled down nicely, and I never have to worry about, what's going on under the hood and then when you run it on your chosen provider, it takes as long as it takes, and it costs what it costs, and you can optimize those at whatever level that you see fit. Yeah, I'm not sure that answers the question as you meant it, but
it's close enough for the purposes of our talk today.
Okay.
And there's only 8 minutes left, and I don't want to monopolize the rest of the time.
Cool. Anyone else? PJ?
Yeah, I guess I left a bookmark in the chat as well. Yeah, I think it might have been when Alex was presenting at the beginning, there was this like column of the good and the bad. And I was expecting to see maybe at the first bullet on the bad as like, we still don't have very many compelling use cases for future quantum computers. And yeah, so I'm wondering if you could assuage my fears that we're going to be good, or if this worry.
Yeah, I mean, I think I guess I share your fear. As someone who works on applications, like it seems like we need to do a better job of finding concrete applications. I mean, to some extent, there's this one bullet about like the gap between resource estimates and useful quantum algorithms. Like you can design these theoretically the algorithms with like a theoretical speed up, but when the speed up is only polynomial, oftentimes the resource estimates are just really not very good. They don't seem like they're going to be very practical. So I would say we could have worded that in maybe the way you said it. That we really need to either identify algorithms with like much larger asymptotic speedups, so that when you do this whole process of resource estimation, you get something that seems like in a reasonable amount of time and effort, you can do something useful for someone. Or we have to take what we have, where we do think that there are some asymptotic speedups, and somehow reduce the overheads involved, either at the level of like gate compilations or reduce the T counts and stuff, or design better quantum error correcting codes that make being able to execute them much better, or make hardware that runs these quantum error correcting codes much faster. But yeah, I mean, I agree that the overall picture is a bit there could be reason for worry. So yeah, I don't necessarily want to disagree with what you said.
Okay, and yeah, also I see what you're saying with the bullet on this gap.
Yeah.
I interpreted that as like there's a gap between today's hardware and where we need to be, but it sounds like you're saying there's also a gap between future hardware and what the resource estimates are.
Yeah, I think it was sort of intentionally vague there, because there's multiple gaps. Yeah. There's gaps between the hardware currently and what the hardware can be in our kind of what we can see that it can be if we just sort of scale up and make things a little bit better. But then there's also a gap between that and resource estimations of useful algorithms. So I guess these could have been separated.
Cool, thank you. Amara/Athena?
Yeah, I want to say thanks again for putting all these resource counts together. And I think you guys have had a lot of experience over the last, I don't know how long this paper took together, but I assume it was at least like a year or so. So I assume you guys have a lot of experience with taking these applications and, bringing them to the quantum space. And I think Alex just mentioned that he is in fact an application scientist, right? So I was wondering, what have you learned during that time in order to sort of smooth out the process from an application to a resource estimate, right? And what are some key steps that you might have identified during your time?
Sam, I don't know, do you have a opinion after the example you gave, I guess?
So maybe a couple of points. One is that we weren't necessarily designing new applications here, which I think made our lives slightly easier. You know, we were able to borrow from all these existing great works and just lay out the work they might have done in a slightly more concise and generic way. Maybe one thing we've noticed is that, you know, we only have a limited set of quantum algorithms and quantum primitives, and they solve these very well-defined mathematical tasks. So I guess coming back to what Alex was saying about this disconnect between the tasks that the quantum computers actually solve and the tasks that people want to solve in real life, it would be helpful to either, you know, find more settings where there are these like real world tasks we want to solve and find a way to very naturally fit them onto quantum computers. Or it might just be that there are, you know, a range of applications out there that we've not noticed yet because people aren't solving them with classical computers and they're not well suited for classical computers, but they might be much better suited for running on quantum devices.
Cool. Think so. Let's do it this way. Exxon will be the last question. Then we'll stop recording, and then whoever can stay on the call, like, feel free to stay on the call and discuss. But like, it's scheduled for an hour, so let's be mindful of people's time. Okay, Exxon.
So, do you hear me? Yeah. Okay. Thank you. Thank you guys for the nice talk. Actually, as a physicist, I mean, I have a few questions regarding to the calculation that you did. You know that the Hubbard model is a very well-known model among like condensed matter physicists. And what I can see here, you took the model from physics and you did some calculation using the quantum computing techniques. But at the end of the day, I just wonder if you managed to get some result in the end, because well, we know that normally people are just looking for the energy, as you just said in the beginning of the talk, just energy density, occupation numbers, and so on. So just wondering if you managed to apply these your method and get some energy or just get some result.
What was the question? Sorry, like, did we run it or?
No, I mean, yeah, if you manage to just run the calculation and get some output, because well, the goal is just to get some output from this method, not just doing some mathematical manipulation and techniques. So just applying to the method to the problem and just get some results. So just wondering if you managed to solve the Hubbard Hamiltonian, and for another question is for what sort of system did you do the calculation? Was it just 1D, 2D, 3D?
Okay,
and,
right.
Yeah.
Yeah, sure. So I guess the idea of the survey and probably a lot of the spirit of this resource estimate community is that if we want to look ahead to when we have fault tolerant quantum computers, we don't have these devices available to us at the moment. So if we want to work out like what resources it will take to run these algorithms, we need to look at things with provable guarantees where we can make these mathematical statements about what resources it will take, and then try and optimize these at present through whatever means we have, so that people in the labs building this hardware, they don't have to build a device with 100 million physical qubits. Maybe they can get away with 1 or 10 million instead. So there are things you can do in the meantime, like you could run NISQ algorithms to try and solve a system like the Fermi-Hubbard model, and obviously people do a lot of that in the literature. But we really wanted to focus on this more like long-term fault tolerant view, where all we can really do at present is do this mathematical reasoning, and we can't try and run things yet.
Okay, thank you. So just out of curiosity, did you do the calculation for 2D material or 2D lattice, or
yeah,
this is just 1D?
This is 2D for the back of the envelope.
Because we know that 1D is simpler. If you want to just at the end of the day you want to just run it and use it just compute with quantum computers. With 1D you can get the result easier and with less qubit. And of course, there are lots of other calculations that you can just compare the result with. For example, exact diagonalization and Monte Carlo calculations. That,
Sure, I guess again, the motivation is to kind of find these problems for which classical computers are really going to struggle, which my understanding is not necessarily the 1D Hubbard model, but the 2D Hubbard model is still hard in many regimes classically. So we were kind of trying to pick problems like this in the survey that are good targets for quantum computers to prove advantageous over classical ones.
All right, fair enough. Thank you. Thanks so much.
Cool. Thank you very much, guys. And I think that's it for the meeting. So stop recording.